The year was 1943, and at Supermarine Aviation Works near Southampton, a brand new Rolls-Royce Griffin engine transformed the legendary Spitfire into an untamable beast. Nearly 2,000 horsepower of pure fury twisted the aircraft like a corkscrew, forcing pilots to wrestle with the controls just to keep the machine flying straight. Every engineer in Britain understood. The solution had to be simple, proven, and reliable. But Joseph Smith had a different idea. 2 propellers, rotating in opposite directions on a single shaft. His own colleagues called it foolishness, a mechanical nightmare, too heavy, complex, and fragile for combat conditions. The Ministry of Aircraft Production wanted nothing to do with Smith's invention. However, when the first modified Spitfire lifted off the runway and reached a speed of 756 kilometers per hour without a single wobble, when test pilots reported such smooth handling that they could thread a needle in a dogfight, suddenly everyone wanted to know how the engineer's silliest idea became the Allies' deadliest secret. So in this video, we'll reveal 3 techniques that will make your designs look visually more expensive. And here's the first one. You make this mistake in every video, but don't notice it. Forget everything they taught you in school. It's a lie. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, don't forget to write in the comments where you're watching from. The autumn rain of 1943 drummed against the roof of the Supermarine Aviation Works hangar, each drop counting down the time Britain couldn't afford to lose. Inside, under the harsh glare of industrial lamps, mechanics toiled feverishly around the sleek fuselage of what was meant to be the Royal Air Force's most formidable weapon. The Spitfire Mark 21 embodied everything the Allies needed: speed, firepower, and the legendary maneuverability that had saved Britain during the darkest days of the Blitz. But something had gone catastrophically wrong. Squadron leader James McKinnon climbed out of the cockpit, his flight suit damp with sweat despite the October chill. His hands trembled slightly as he removed his leather gloves, not from fear, but from the sheer physical exhaustion of wrestling with 2,000 horsepower of barely controlled fury in the skies over Hampshire. The new Rolls-Royce Griffin engine had transformed his beloved Spitfire into something that felt more like riding an unbroken horse than flying an aircraft. "How bad is it?" asked Chief Engineer Malcolm Whitfield, already reading the answer in McKinnon's expression. "At 560 kilometers per hour, it wants to roll so hard to the left I nearly spun out," McKinnon replied, his Scottish accent thick with frustration. "The torque from that bloody enormous engine. It's like the propeller is trying to rip the nose clean off the plane. And above 640 kilometers per hour. Forget about it. No pilot in the world could keep her straight in a combat situation." The figures painted a grim picture. The Griffin 65 engine produced 1,850 horsepower at sea level, nearly double that of the original Merlin engine fitted to earlier Spitfire variants. This raw power was supposed to propel the aircraft to over 756 kilometers per hour, making it faster than any German fighter in the sky. Instead, the massive reactive torque, the equal and opposite force described by Newton centuries ago, twisted the entire airframe with such violence that pilots couldn't maintain level flight at combat speeds. Whitfield ran a hand over the propeller hub, feeling the faint vibration that never quite ceased even when the engine was off. The engineering challenge was brutally simple in concept, but incredibly complex in execution. Every rotation of that massive four-bladed propeller generated a rotational force that tried to spin the aircraft in the opposite direction. At low speeds, pilots could compensate with rudder input and brute strength. But as airspeeds increased, aerodynamic forces exponentially amplified the problem. The result was an aircraft that became increasingly dangerous to fly the faster it went, precisely the opposite of what was needed in combat. The Germans have the same problem with their powerful fighters, Whitfield said, though there was no comfort in his tone. Their Focke-Wulf 190 series suffers from similar torque issues, but they've learned to work around them through pilot training and tactical limitations. McKinnon shook his head sharply. We can't work around physics, Malcolm. This isn't about flying technique or training protocols. At the speeds we need for air superiority over Western Europe, this aircraft is simply unflyable. And if we can't solve this problem... He left the sentence unfinished. Everyone in that hangar understood what was at stake. The Ministry of Aircraft Production had already invested millions of pounds sterling in the development of the Griffin engine and the redesign of the Spitfire airframe to accommodate its increased size and weight. Production schedules called for hundreds of these aircraft to roll off assembly lines within months. The Royal Navy desperately needed a navalized variant, the Seafire, to match the performance of American carrier-borne fighters in the Pacific theater. Failure was not just an engineering setback. It represented a potentially catastrophic gap in Allied air power at the most critical stage of the war. 15 miles away, in the cluttered office of Rotoll Airscrews Limited, Joseph Smith sat surrounded by technical drawings, slide rules, and empty teacups. The chief designer had spent the last week poring over flight test data from the troubled Spitfire, searching for a solution that his colleagues increasingly believed didn't exist. All traditional approaches had failed. Increasing rudder size added weight and drag without addressing the fundamental issue. Modifying engine mounts to reduce torque transfer weakened the airframe structure. Adjusting propeller blade angles helped marginally, but introduced new problems with efficiency and vibration. Smith's reputation in the aviation industry was complex. At 42, he possessed an intuitive understanding of aerodynamics bordering on genius. Yet his solutions often seemed overly complex or impractical to more conservative engineers. He had designed propeller systems for Rolls-Royce that pushed the boundaries of what manufacturing technology could achieve, earning reluctant respect for their performance and equally vocal criticism for their production challenges. His colleagues at Rotoll had learned to expect the unexpected from Smith, though few were prepared for what he proposed that gray October day. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, don't forget to write in the comments where you're watching from. On that October afternoon, as the world choked in the fires of global war, one man proposed a solution that many considered madness. Have you ever wondered if even the greatest engineering minds sometimes miss the obvious? That a solution capable of turning the tide of war could be dismissed as a Rube Goldberg machine. Perhaps you too have faced situations where your idea, however brilliant it seemed, met a wall of misunderstanding and skepticism. We know that feeling. But the story we'll tell today will show how, even in the most critical conditions, one person's courage can change everything. In this video, we'll delve into the history of one of the most unusual yet critically important engineering systems of World War II, the contra-rotating propeller for the legendary Spitfire. Do you think the Spitfire was perfect? Well, even this icon had its Achilles heel, which threatened its air superiority, and the answer to this problem was so audacious that it was initially deemed madness. And here's how it all began. The concept originated in Smith's mind, who deeply understood torque not as an undesirable problem to suppress, but as a fundamental force that could be harnessed. Instead of fighting the colossal rotational energy of the Griffin engine, he proposed taming it with a system of coaxial contra-rotating propellers. Two propellers, mounted on the same shaft but rotating in opposite directions, were designed to mutually cancel out the torque reaction while providing unprecedented thrust efficiency. This was meant to open a new chapter in aviation history, if only his convictions were accepted. The engineering challenges facing the developers were astounding. The system required a complex gearbox to drive both propellers from a single engine, adding weight and mechanical complexity to an aircraft already operating at the limits of its structural integrity. The coaxial propellers had to be precisely balanced to prevent catastrophic vibrations, and the entire assembly had to withstand the immense stresses of combat maneuvering. Most importantly, the system had to be robust enough for mass production and field maintenance under wartime conditions. When Smith first presented his drawings to the Roddle engineering team, the reaction was immediate and overwhelmingly negative. Senior engineer Robert Morrison called it a Rube Goldberg mechanical machine that would be impossible to produce in large quantities. Production manager Charles Henley worried about the weight penalty and maintenance requirements. Test engineer David Clark doubted whether the system could withstand the stresses of carrier operations for the Naval Seafire variant. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, don't forget to write in the comments where you're watching from. It's just too complex, Morrison argued during a heated meeting in Smith's office. We're talking about essentially building two complete propeller systems and somehow making them work perfectly together. The gear ratios alone would require manufacturing precision that we can barely achieve in peacetime, let alone under the pressures of wartime production. But Smith had already done his calculations. The contra-rotating system would indeed be heavier than a conventional single propeller, approximately 90 kilograms, about 200 pounds, more. But eliminating torque reaction would allow the aircraft to achieve its full speed potential. More importantly, the improved efficiency of the propellers would actually increase thrust by nearly 15%, more than compensating for the additional weight. The Spitfire Mark 21 could finally become the 756 km/h interceptor, the RAF so desperately needed. As autumn turned to winter, the debate over Smith's foolish propeller design was set to determine not only the fate of Britain's most famous fighter, but also the balance of air power over the battlefields of Europe and the Pacific. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, don't forget to write in the comments where you're watching from. The Ministry of Aircraft Production boardroom in London resembled a tribunal more than an engineering conference when Smith arrived on the morning of November 15, 1943. Seated around the mahogany table were some of Britain's highest-ranking aviation officials, their faces bearing the weight of a war that had already consumed 4 years and showed no sign of ending soon. Air Chief Marshal Sir Wilfrid Freeman presided over the meeting with the grim efficiency of a man who had seen too many promising aircraft projects fail when they were needed most. "Mr. Smith," Freeman began, his voice imbued with the clipped authority of the Royal Air Force, "we have reviewed your proposal for this coaxial contra-rotating propeller system. I must say, the initial reaction from our technical staff has been skeptical." He gestured towards a stack of reports that seemed to tower over Smith's modest folder of drawings. "The consensus appears to be that your design introduces unnecessary complexity at precisely the moment we need proven, reliable solutions." Smith had anticipated this resistance, but the formal setting made his throat tighten with nervous tension. These men controlled the fate of British aviation, and their decision would determine whether his months of calculations and sleepless nights amounted to anything more than an academic exercise. "Sir, with all due respect, I believe the system's complexity is precisely what makes it effective. We are not merely adding components. We are fundamentally solving the torque problem that has rendered the Griffin engine unusable at combat speeds." Director of Technical Development. Sir Roy Fedden leaned forward, his reputation as one of Britain's most distinguished engine designers lending weight to his skepticism. "Mr. Smith, your proposal calls for a gearbox system that would make this propeller assembly the most complex ever fitted to a fighter aircraft. We are talking about coaxial contra-rotating shafts, a planetary gear system, and precise synchronization that must remain perfect under combat conditions. The maintenance requirements alone could ground entire squadrons." The figures Smith had prepared told a different story, but he knew that raw data alone wouldn't be enough to overcome institutional inertia. "The gearbox complexity is manageable, with proper manufacturing tolerances. De Havilland has already proven that complex propeller systems can be mass-produced with their variable pitch mechanisms. Our system would utilize a 2-stage planetary gear train with a ratio of 0. 77:1 for the front propeller, and 0. 62.1 for the rear. The differential rotation speeds would be precisely calculated to cancel torque, while maximizing thrust efficiency." Group Captain Peter Thornton, representing operational requirements, flipped through a folder of combat reports from the Mediterranean and Pacific theaters. "Even if your system works mechanically, Mr. Smith, we are concerned about weight and balance. The Mark 21 is already heavier than previous Spitfire variants. Adding 90 kilograms, about 200 pounds, of additional propeller hardware could affect performance in ways we don't fully understand." Smith had anticipated this objection and pulled out his most carefully prepared calculations. "The weight penalty is real, sir, but the performance gains more than offset it. Our estimates show a 15% increase in thrust combined with the complete elimination of torque reaction. The aircraft will not only achieve its projected speed of 756 km/h, but will also maintain controllable flight characteristics across its entire speed envelope. Current test flights show the Mark 21 becoming increasingly dangerous above 563 km/h. Our system will significantly extend safe operation beyond 640 km/h. Imagine this situation. You are a brilliant engineer whose bold idea could change the course of the war, but your colleagues call it foolish. Sound familiar? Surely each of us has at some point faced innovative thoughts being rejected, meeting a wall of skepticism. But what if this foolish idea is the only hope for victory when the enemy is breathing down your neck? In this video, we will unveil an incredible chapter in the history of the legendary Spitfire fighter that remained in the shadows, and show how one decision, defying all established rules, was meant to secure Allied air superiority. You will learn about 3 key moments that made this breakthrough possible. And the first one will literally make you rethink everything you thought you knew about aviation. In 1944, as the shadow of an impending invasion loomed over Western Europe, intelligence gathered through ultra-intercepts painted a troubling picture. German designers at Messerschmitt were actively developing high-speed modifications of their Me-262 jet fighter, while Focke-Wulf continued to refine their high-altitude Ta-152s. The Allies desperately needed every advantage in speed and maneuverability to maintain air dominance. It was at this critical juncture that a proposal, audacious to the point of seeming insane, was made. Tension hung in the air as Freeman, the chief official, reviewed his notes, carefully weighing the technical risks against operational needs. Smith's proposal, coming from a distinguished engineer, would require significant changes to existing production lines. How long would it take to develop a working prototype, assuming we approve the project? He asked, his voice betraying a hidden concern. Smith's reply was confident, yet it masked colossal engineering complexities. 6 weeks for initial design and gearbox fabrication, sir. Another 4 weeks for propeller manufacture and balancing. By early February, we could have a ready unit for flight testing. Stay with us and watch until the end, because what you're about to learn will change your perception of human and machine capabilities. We'd be especially grateful for a like and a subscription, and don't forget to write in the comments where you're watching from. Smith's confidence, however, could not conceal the enormous technical barriers. The coaxial contra-rotating propeller system demanded jeweler-like precision, exceeding Britain's manufacturing capabilities at the time. Each propeller had to be individually balanced to fractions of an ounce, and the gearbox required the same tooth-cutting accuracy typically applied to marine chronometers. Silence filled the room as the officials digested the proposed timeline. 6 months had passed since the first problematic flight tests of the Griffin-powered Spitfire, Mark 21, and pressure from operational squadrons was mounting. Pilots demanded aircraft that could match or surpass German fighter performance, especially at high altitudes where the Griffin engine's power advantage should have been decisive. Air Commodore Ralph Sorley, who had overseen fighter development throughout the Battle of Britain, finally broke the silence that seemed to weigh on everyone present. And before we continue our dive into this captivating story, we'd like to ask you once more, stay with us and watch until the end. Your like and subscription are the best reward for us. And of course, don't forget to mention in the comments from which part of the world you are watching us. Mr. Smith, your reputation suggests that when you propose something so unconventional, it warrants serious consideration. Sorley began, staring intently at the engineer. But I must ask you directly, are you absolutely certain this system will work? We cannot afford another failed modification program. Smith met his gaze. Sir, I am staking my career on it. The physics are impeccable. The engineering solutions are achievable. and the performance gain is precisely what the Royal Air Force needs. The Spitfire Mark 21 with contra-rotating propellers will become the fastest and most maneuverable fighter in the world. This bold statement hung in the air like a challenge to fate. Freeman exchanged glances with his colleagues, recognizing that Smith's confidence was underpinned by genuine technical genius. This was the man who had designed propeller systems for Britain's most successful aircraft, and his track record showed that his unorthodox solutions often triumphed where traditional approaches had failed. "Very well," Freeman finally conceded. "We will authorize a limited development program, one prototype installation, full flight testing, and a complete performance evaluation. But understand, Mr. Smith, if this system fails, or if it delays Mark 21 production by even a month, the consequences will extend far beyond your career." As Smith gathered his papers, preparing to leave, he felt the weight of responsibility settle upon his shoulders like a lead blanket. The coming months would determine whether his foolish design would become a revolution in fighter aviation or merely another cautionary tale about the perils of engineering hubris. Either way, the legacy of the Spitfire, and perhaps the outcome of the air battles over Europe, now depended on gears, shafts, and propellers rotating in directions that defied all conventional notions of aircraft design. War did not wait for perfection, but it might just reward the kind of radical thinking that turned impossible ideas into combat reality. The morning of February 23, 1944, dawned gray and raw over Salisbury Plain, with winds reaching 25 knots at the experimental airfield of Boscombe Down. Inside Hangar 7, a modified Spitfire Mark 21 sat among its conventional brethren, like a mechanical alien. The massive contra-rotating propeller assembly dominated its nose, giving it an almost predatory appearance. The two propellers, each 11 feet in diameter, created a visual illusion that seemed to defy the fundamental laws of aeronautical engineering. Test pilot squadron leader Jeffrey Whelm approached the aircraft with the focused attention of a man who understood he was about to risk his life for an unproven theory. At 24, Whelm had already survived 3 years of combat sorties over Britain, France, and Malta, logging nearly 800 hours in various Spitfire marks. His reputation for precise aircraft evaluation had earned him assignments to the most experimental programs. Yet nothing in his experience had prepared him for the mechanical complexity now bolted to the nose of Spitfire serial number RK958. The contra-rotating propeller system was the culmination of 6 months of intensive engineering by Smith's team at Rotol. The front propeller rotated clockwise at 1,825 revolutions per minute, while the rear propeller spun counterclockwise at 1,475 revolutions per minute. Between them sat a 193-pound gearbox, machined with a precision usually reserved for fine watch movements. Every component had been balanced to within half an ounce, yet the entire assembly still vibrated with a frequency that seemed to pulse through the airframe like a mechanical heartbeat. Chief Test Engineer Michael Lithgow oversaw the pre-flight inspection with a nervous energy that infected everyone in the hangar. Gearbox temperatures remained within limits during ground runs, he reported to Whelm, consulting a notepad filled with data tables. Oil pressure maintained 60 psi across the power range. But Jeffrey, we're still seeing harmonic vibrations at 1/800 engine RPM that we can't fully account for. Each of us has, at least once, stood on the brink of a great discovery or a catastrophic failure. This fine line, where hope clashes with uncertainty is familiar to many. Today, we'll tell a story where that line was sharper than a razor's edge, a story that could have changed the course of aviation, but instead confronted a ruthless reality no one could have predicted. Imagine investing years of your life, every drop of your energy, into a project that promises a revolution. You believe in it with all your heart, but deep down, a fear lingers. What if everything goes wrong? It was with such thoughts that engineers and pilots awaited their moment that morning when the legendary Spitfire was to take to the sky with a never-before-seen design. Do you think you know the story of this famous fighter? Forget everything you've been told about its perfect characteristics. Today, we will uncover the secrets of a maiden flight that was meant to make it even more perfect, but instead revealed entirely new, frightening facets. In this video, we will delve into the details of the day, innovation met brutal reality, and show how one seemingly minor detail could dramatically alter the fate of a legend. We will highlight 3 key moments that defined this flight, and the first of them manifested even before takeoff. Stay with us until the end to learn all the details of this captivating story. We'd be especially grateful for a like and a subscription, as it helps us create more content like this. And of course, tell us in the comments where you're watching from. We're always interested to know our geography. Pilot Whelm, surveying the intricate contra-rotating propeller system, felt a mixture of awe and apprehension. It looked incredibly complex compared to the sleek simplicity of conventional single-propeller installations. His hand brushed against the propeller hub, and he involuntarily nodded, recognizing the scale of engineering genius encapsulated in the mechanism and its potential for unpredictable surprises. "What's our test plan?" Whelm asked, turning to Chief Engineer Lithgow. "We've opted for a conservative approach," Lithgow replied. "Climb to 8,000 feet, level flight at various power settings, then a gradual increase in speed up to 400 miles per hour, provided the aircraft remains manageable. Our particular focus is on torque reaction characteristics and any unusual handling qualities that might emerge." Designer Smith stood near the aircraft's left wing, his face betraying none of the anxiety that had kept him awake for the past week. This morning was the culmination of his professional career, yet it also held the potential for catastrophic failure that could ruin not only his reputation, but also Whelm's life. Every calculation had been double-checked, every component tested to its breaking point. And yet, aircraft design remained an art as much as a science, holding its own unsolved mysteries. At precisely 9:15 a.m., Whelm strapped into the familiar Spitfire cockpit, though the instrument panel now included additional gauges to monitor the complex propeller system. Engine oil temperature, gearbox oil pressure, and front and rear propeller pitch. Each of these parameters demanded constant attention during what should have been a routine flight. The Rolls-Royce Griffin engine roared to life with its characteristic deep rumble, but the sound was immediately transformed by the contra-rotating propellers into something entirely new. Instead of the familiar rhythmic pulse of a single propeller, the twin assemblies created a complex harmonic that seemed to vibrate through the pilot's bones. Ground control cleared Whelm for takeoff at 9:32 a.m., and he advanced the throttle with deliberate caution. The Spitfire began its roll with surprising smoothness. The contra-rotating propellers completely eliminated the usual left-turning tendency that every Spitfire pilot had learned to compensate for with right rudder input. For the first time in months of Mark 21 testing, the aircraft tracked perfectly down the center line of the runway, without constant pilot correction. Liftoff occurred at 85 miles per hour, precisely as predicted, but Whelm immediately noticed something amiss. The aircraft felt sluggish on the climb, requiring more power than anticipated to maintain a reasonable rate of ascent. The added weight of the propeller system was clearly impacting performance more significantly than Smith's calculations had suggested. By the time Whelm reached 5,000 feet, he was using nearly full throttle to maintain a 2,000 feet per minute climb rate, a performance that should have been easily achievable at 75% power. Stay with us and watch until the end, because the most interesting part is yet to come. We would be especially grateful for a like and a subscription. And of course, don't forget to write in the comments where you are watching this video from. Boscombe Control. This is Test 27, Whelm. He radioed. I'm experiencing higher than expected power requirements for normal climb performance. Requesting permission to level off at 6,000 feet for handling evaluation. The reply crackled immediately in his headset. Test 27. You are cleared for level flight. How's she handling? Whelm reduced power to cruising settings and was surprised by the aircraft's response. Despite the climb issues, the Spitfire felt remarkably stable in level flight. The elimination of torque reaction had altered the aircraft's handling characteristics in ways that went far beyond mere directional control. The entire airframe felt more solid, more predictable, as if the contra-rotating propellers had somehow tamed the wild energy of the Griffin engine. At 300 miles per hour, an aircraft that previously tried to roll uncontrollably now flew with the rock-steady precision of a much smaller, less powerful fighter. Whelm experimented with gentle turns, steep banks, and rapid changes of direction, finding that the Mark 21 responded with a nimbleness that seemed impossible for such a large and heavy aircraft. The removal of torque reaction had restored the legendary Spitfire handling that had made the type famous during the Battle of Britain. But as Whelm increased the throttle to maximum power, the aircraft's performance became truly alarming. Instead of smoothly accelerating towards its theoretical top speed, the Spitfire began to vibrate with increasing intensity. At 370 miles per hour, the entire airframe shook so violently that Whelm could barely read his instruments. The contra-rotating propellers, designed to work in perfect harmony, seemed to be creating destructive interference patterns that threatened to tear the aircraft apart. Boscombe Control. Test 27 is experiencing severe vibration above 370 miles per hour, Whelm reported. His voice strained with concentration as he reduced power to bring the shaking under control. I am returning to base for an emergency landing. The approach for landing revealed yet another unexpected characteristic of the modified aircraft. With power reduced to idle, the Spitfire descended much faster than usual, requiring constant throttle adjustments to maintain the correct glide slope. The added weight and altered aerodynamic characteristics of the contra-rotating propeller system had fundamentally changed the aircraft's flight performance in ways Smith's team had not fully anticipated. Whelm landed at Boscombe Down after 43 minutes of flight testing, his face grim with the realization that Smith's revolutionary design had failed its crucial first test. The contra-rotating propellers had performed as claimed in eliminating torque reaction, but they had introduced new problems that might prove even more dangerous than the original Griffin engine difficulties. As ground crews inspected the aircraft, checking for structural damage from the severe vibrations, Smith approached Whelm with the expression of a man watching his life's work crumble. The test pilot's report would determine whether the contra-rotating propeller project would continue or join the long list of promising aviation innovations that never survived their first encounter with reality. Imagine this. You've invested months of hard work, hundreds of calculations, your very reputation, and then everything crumbles in an instant. Do you know that feeling when a grand idea collides with harsh reality? We once faced that same sense of hopelessness, when it seemed all efforts were in vain. But, as in the story we are about to tell, even from the deepest failures, a way out can be found. In this video, we'll dive into a critical moment in aviation history when a brilliant engineering concept clashed with unpredictable reality, and discover how a team struggled to save a project. What if I told you that solving one problem could give rise to another, far more dangerous? Just 2 hours after pilot Whelm's landing, an emergency meeting was convened in Hangar 7. Engineer Smith found himself at the center of a circle formed by engineers, test pilots, and ministry officials, whose faces reflected a spectrum of emotions, from deep disappointment to barely concealed anger. Behind them, in complete silence, stood the modified Spitfire, its contra-rotating propellers now still, yet still exuding an aura of mechanical menace, like a lurking predator. Immediately after receiving the preliminary report, Air Commodore Sorley arrived from London, and his presence instantly transformed a routine technical debriefing into something more akin to a court-martial. This was the first encounter with the harsh truth. "Squadron Leader Whelm," Sorley began, his voice imbued with the full weight of bureaucratic authority. "I ask you to present us with a full assessment of the aircraft's performance during today's test flight." Whelm snapped to attention, though his flight suit still bore the sweat marks from a desperate struggle with a machine that had nearly disintegrated in midair. "Sir, the contra-rotating propellers completely eliminated torque reaction during takeoff and low-speed flight. The aircraft tracked straight down the runway without any rudder input, and handling at speeds below 300 miles per hour was exceptional, perhaps the best of any Spitfire variant I have ever flown." A murmur of surprise ran through the assembled engineers. Despite the flight's dramatic conclusion, Whelm's initial assessment suggested that Smith's basic concept had successfully addressed the Griffin engine's primary challenge, the torque problem. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, tell us in the comments where you're watching this video from. "However," Whelm continued, his tone becoming more somber, "above 370 merom, the aircraft experienced severe vibrations that made further speed increases impossible. The entire airframe shook so violently that I feared structural failure. Additionally, climb performance was significantly degraded. We required nearly full power to achieve climb rates that should have been possible at 75% throttle." Smith felt the weight of failure settling on his shoulders like a lead blanket. 6 months of calculations, manufacturing precision, and professional reputation had produced an aircraft that performed brilliantly at low speeds, but became uncontrollable, precisely when maximum performance was needed most. The irony was bitter. He had solved the torque problem only to create vibration issues that were potentially more dangerous than the original difficulties. And this, as we will see, was only the beginning of new challenges. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, tell us in the comments where you're watching this video from. Chief Engineer Lithgow carefully consulted his clipboard of technical data, searching for explanations that might salvage something from the day's disaster. Our ground-running tests had shown harmonic vibrations at specific engine speeds, but nothing approaching the severity Squadron Leader Whelm experienced in flight. The aerodynamic loads at high speeds seemed to be exciting resonances in the propeller system that we hadn't anticipated. Director Fedden leaned forward, his reputation for technical precision making his questions particularly pointed. "Mr. Smith, your original calculations presumably accounted for aerodynamic forces on the propeller assemblies. How do you explain this discrepancy between predicted and actual performance?" This was the pivotal question, an answer to which could determine the fate of the entire project. Smith had spent the past 2 hours analyzing precisely this question, and his answer revealed the fundamental complexity of aviation engineering during wartime. "Sir, our calculations were based on static ground testing and wind tunnel data. The interaction between two contra-rotating propellers in actual flight conditions, particularly at high airspeeds, creates aerodynamic phenomena that are extremely difficult to predict without actual flight testing. The propeller tip vortices appeared to be creating destructive interference patterns that weren't apparent in our laboratory work. The explanation was technically accurate, but offered little comfort to officials who had invested months and considerable resources in Smith's experimental design." Air Commodore Sorley's expression suggested that he was already calculating the political consequences of another failed aircraft modification program, and the threat of the project's cancellation hung heavy in the air. "The question now," Sorley said grimly, "is whether these problems can be solved within a reasonable time frame, or whether we should abandon this approach entirely and focus on conventional solutions to the Griffin's torque issues." Smith felt his career hanging in the balance, but his engineer's instincts refused to accept defeat without exploring every possible solution. "Sir, I believe the vibration problems can be resolved through modifications to the propeller blade design and gearbox timing. The fundamental concept remains sound. We simply need to eliminate the aerodynamic interference that's causing the destructive resonance." Test pilot Whelm, despite having risked his life in the morning's flight, found himself unexpectedly supporting Smith's position. "With respect, sir, the aircraft's handling below 370 mph was remarkable. If Mr. Smith can solve the high-speed vibration issue, we could have an aircraft that combines the Griffin's power with handling characteristics that exceed any fighter currently in service." This was a ray of hope that could change everything. The room fell silent as the officials weighed the competing demands of technical perfectionism against operational urgency. Allied intelligence reports indicated that German aircraft manufacturers were rapidly developing new high-performance fighters. While the invasion of Western Europe, still months away but already consuming enormous planning resources, would require absolute air superiority over the battlefield. Smith seized the moment of uncertainty to present his proposed solution. The vibration analysis suggests that the problem lies in the relationship between propeller blade angles and rotational speeds. By adjusting the gear ratios to alter the speed differential between forward and rear propellers, we can shift the harmonic frequencies away from the critical resonance points. Additionally, modifying the blade twist distribution should reduce tip vortex interaction. Lithgow looked up from his calculations with cautious optimism. The modifications Mr. Smith describes would require approximately 3 weeks of machine shop work and another week for rebalancing the entire system. We could have the aircraft ready for second phase testing by mid-March. Thus, a prospect, though fraught with risk, still offered a chance for success. The question now, Sorley grimly stated, is whether these issues can be resolved in a reasonable time frame, or if we should abandon this approach entirely and focus on traditional solutions for the Griffin's torque problems. Smith felt his career hanging by a thread, but his engineering instincts refused to accept defeat without exploring every possible solution. "Sir, I believe the vibration issues can be eliminated by modifying the propeller blade design and synchronizing the gearbox. The fundamental concept remains viable. We simply need to eliminate the aerodynamic interference causing the destructive resonance." Test pilot Whelm, despite having risked his life in the morning's flight, unexpectedly supported Smith's position. "With all due respect, sir, the aircraft's handling at speeds below 370 miles per hour was outstanding. If Mr. Smith can resolve the high-speed vibration problem, we could have an aircraft that combines the Griffin's power with handling characteristics superior to any fighter currently in service." This was a ray of hope that could change everything. A silence fell over the room as officials weighed the conflicting demands of technical perfectionism and operational urgency. Allied intelligence reports indicated that German aircraft manufacturers were actively developing new, high-performance fighters. The invasion of Western Europe, still months away, but already consuming vast planning resources, demanded absolute air superiority over the battlefield. Smith seized the moment of uncertainty to present his proposed solution. Vibration analysis suggests the problem lies in the interrelationship between propeller blade angles and rotation speeds. By adjusting gear ratios to alter the speed difference between the front and rear propellers, we can shift the harmonic frequencies away from critical resonance points. Additionally, modifying the blade twist distribution should reduce vortex interaction at their tips. Lithgow looked up from his calculations with cautious optimism. The modifications Mr. Smith described will require approximately 3 weeks of work in the machine shop and another week for rebalancing the entire system. We could have the aircraft ready for a second phase of trials by mid-March. Thus a prospect, though fraught with risk, still offered a chance for success. Have you ever wondered what distinguishes an ordinary design from one that screams, "This is expensive"? If you've ever found yourself thinking your project looks good, but lacks that spark of premium quality that makes clients gasp with delight, then this content directly addresses your pain. I've been there myself, on the other side of the screen where every pixel seemed perfect. Yet something was missing. And today we're going to break down not just techniques but genuine secrets that once helped me too. It's no secret that from the very first moments, we're obligated to capture your attention, to justify every second you choose to spend with us. That's why today we're going to reveal something many designers aren't even aware of. For example, in this video, you'll learn 3 tricks that will instantly make your design visually more expensive. And here's the first one. By the way, you're making a very common mistake that subtly undermines the value of your work. You don't even realize how much it affects the perception of your design. Intrigued? Forget everything you've been taught about good taste in design. Most of those rules are outdated or simply false. Ready to break the mold and learn the truth. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, let us know in the comments where you're watching from. So, we've understood the importance of starting a video, but what comes next? Here, the endless hook takes center stage. This isn't just a sequence of topics, but a continuous flow where each segment seamlessly transitions into the next, leaving a subtle hint of what's to come. The viewer shouldn't feel abrupt shifts. For them, it should be one cohesive story where one discovery logically leads to another, maintaining unwavering interest. All these blocks and sections exist only for us, the creators, on paper. But for the audience, there's only a captivating narrative they want to watch to the end. Let's return to our story. Joseph Smith, an engineer with unconventional thinking, faced the ultimate test. In mid-March, his system was due for its second phase of trials. Air Commodore Sorley, consulting his pocket watch, meticulously calculated the time, understanding that every week spent on experimental refinements delayed the deployment of squadrons that could be vital over Europe. "Mr. Smith," Sorley finally said, "you have one more opportunity to prove the effectiveness of your system. But understand this. This is the absolute limit of our patience for experimental approaches. If the second test flight does not demonstrate clear improvements, we will completely abandon the coaxial propeller program and focus our resources on traditional torque reduction methods." As the meeting concluded, Smith remained in the hangar, gazing at the silent Spitfire, which was both his greatest technical achievement and his most humbling professional failure. The aircraft looked deceptively ordinary, its revolutionary propeller system appearing simply as another piece of machinery awaiting modification. But Smith's engineering eye already envisioned the changes needed to transform his partially successful experiment into the victorious weapon he had originally conceived. The next 3 weeks would determine whether Joseph Smith's foolish idea would become a revolution in fighter aviation or a cautionary tale about the dangers of challenging conventional wisdom in wartime. Either way, the fate of Britain's most famous fighter now depended on gear ratios, blade angles, and the complex physics of rotating propellers that most pilots never bothered to understand. In the deepening twilight of a February evening, Smith began sketching the modifications that would either vindicate his radical thinking or forever end his career in the aviation industry. The morning of March 18, 1944, brought clear skies and calm winds to Boscombe Down, conditions that seemed almost too perfect for what everyone understood to be the final trial of Smith's controversial propeller system. 3 weeks of intense modifications had transformed the coaxial assembly into something that looked subtly different from its initial configuration. While the changes were invisible to those not intimately familiar with propeller blade geometry and gearbox ratios, Smith had spent sleepless nights recalculating every aspect of the system, focusing especially on the harmonic frequencies that had nearly torn the aircraft apart during its first test flight. The solution involved altering the rotational speed ratio of the two propellers from the original 1825 and 1475 RPMs to a new configuration of 1700 and 1500 RPMs, respectively. The closer speed difference would shift critical resonant frequencies outside the aircraft's normal operating range while maintaining the torque compensating effect that made the system valuable. Beyond this, Smith's team had modified the blade twist distribution on both propellers, reducing the aggressive angle changes at the tips that contributed to vortex formation. Each blade now featured a smoother transition from root to tip, designed to minimize the aerodynamic interference that had created destructive vibrations at high speed. The modifications required hand-finishing each blade to tolerances measured in thousandths of an inch, a task that consumed 2 weeks of painstaking craftsmanship. Squadron Leader Whelm approached the modified Spitfire with cautious optimism, tempered by vivid memories of the tumultuous end of his previous flight. From a distance, the aircraft looked identical, but closer inspection revealed the subtle changes that could transform it from a dangerous experiment into a revolutionary weapon. The propeller blades caught the morning light differently, the revised geometry creating shadow patterns that seemed somehow more purposeful than those of the original configuration. The gearbox modifications passed ground testing perfectly, reported Chief Engineer Lithgow, though his voice carried the tension of a man who understood that ground tests meant nothing until validated in actual flight conditions. We maintained stable operation throughout the power range without the harmonic vibrations that plagued the original system. Oil temperatures remained within normal limits, and the new gear ratios eliminated the resonant frequencies we identified in the failure analysis. Air Commodore Sorley had returned from London specifically to witness this second trial, bringing with him a sense of institutional finality that impacted everyone present. The Air Ministry could not afford to endlessly pursue experimental programs, especially when conventional aircraft were desperately needed for the anticipated invasion of Europe. This flight was to determine not only the fate of Smith's propeller system, but also the potential future direction of British fighter development. Precisely at 10:15 a.m., Whelm started the Rolls-Royce Griffin engine and immediately noticed differences from the previous trial. The sound was subtly different, still the complex harmonic produced by coaxial propellers, but somehow more controlled, less aggressive in its mechanical resonance. Engine instruments showed normal readings as he advanced power for taxiing, and the aircraft tracked straight without the slight vibration that had characterized the original system, even during ground operations. The takeoff at 10:28 revealed the most dramatic improvement. Where the previous flight had required near full thrust to achieve an acceptable climb rate, the modified aircraft now gained 2,000 feet per minute, using only 80% power. The revised propeller geometry had seemingly eliminated much of the aerodynamic inefficiency that plagued the original design, allowing the full power of the Griffin engine to translate into actual aircraft performance. Imagine a moment when familiar boundaries crumble, when what was considered the limit of possibility suddenly turns out to be just a starting point. Perhaps each of us has faced that feeling when our own ambitions or projects hit an invisible wall that seemed absolutely insurmountable. Remember that feeling when you gave your all, but the result was far from ideal, and solutions seemed exhausted? We know that pain. We've experienced it. But today we'll show you how to break through that ceiling. In this video, we'll unveil the story of a triumph that proved even the boldest ideas can not only work, but also exceed the wildest expectations, turning established notions upside down. You probably don't even realize the fundamental mistake many make when trying to improve what already exists, instead of completely rethinking it. Forget everything you've been taught about gradual improvements. Today we're talking about a radical breakthrough that didn't just improve an aircraft, but created something entirely new. Now let's fast forward to the day these ambitions collided with reality. Boscombe Control, Test 27 gaining altitude, passing 8,000 feet. Whelm's voice crackled over the radio, tinged with restrained excitement. Climb performance significantly improved over previous trial. Handling remains excellent. Requesting clearance for speed range check. The reply was immediate. Test 27. You are cleared for speed trials. Exercise extreme caution approaching previous problem areas. This wasn't just a formality, it was a reminder that just 3 weeks prior, it was at these very speeds that the aircraft had nearly cost Whelm his life, transforming into an uncontrollable projectile. Before we continue our thrilling account of the flight that changed aviation history, we ask you, stay with us and watch until the very end. We'd be especially grateful for your like and subscription, as it helps us create even more content like this. And of course, let us know in the comments where you're watching this video from. We're very interested to learn the geography of our audience. Whelm leveled the Spitfire at 10,000 feet and began a cautious exploration of the speed range that had nearly killed him just 3 weeks prior. At 300 miles per hour, the aircraft flew with the same smooth precision he remembered from the best conventional Spitfires. At 350 miles per hour, there were still no unusual vibrations or handling anomalies. As the airspeed indicator slowly crept past 370 miles per hour, the speed at which the original system became uncontrollable. Whelm held his breath, bracing for the violent shaking that had forced his emergency return last time. Instead, the Spitfire continued to accelerate smoothly. At 400 miles per hour, the aircraft felt more stable than most fighters at half that speed. The elimination of torque reaction, combined with the resolution of the vibration issues, had given birth to something unprecedented in aviation. A powerful fighter that actually became more controllable as it approached its maximum operational range. Boscombe Control Test 27 has reached 410 miles per hour, with no adverse handling characteristics, Whelm reported, his voice now conveying genuine excitement rather than his previous caution. The aircraft is absolutely stable and responsive. This is outstanding performance. From the control tower, Smith watched through binoculars as his modified Spitfire carved precise turns against the blue Hampshire sky. The counter-rotating propellers were transforming the colossal power of the Griffin engine into speed and maneuverability that seemed to defy the very laws of aeronautical physics. The sight vindicated not only months of painstaking engineering, but also his fundamental belief that conventional approaches were insufficient for the challenges of modern warfare. Whelm continued the trials for another 25 minutes, exploring every aspect of the aircraft's operational envelope. High-speed dives showed that the Spitfire could exceed 450 miles per hour in a controlled descent without developing the compressibility issues that affected many high-performance fighters. Steep turns at maximum power demonstrated handling that combined the agility of earlier Spitfire variants with the raw performance of the Griffin engine. Landing at 11:32 a.m., Whelm taxied to the hangar with the expression of a pilot who had just experienced something truly revolutionary. As he shut down the engine and climbed out of the cockpit, his first words to the assembled engineers and officials carried the weight of professional experience earned over years of combat flying. "Gentlemen," Whelm announced, removing his flying helmet and looking directly at Smith, "what you have created is not just an improved Spitfire. It is the finest fighter I have ever flown. The combination of speed, handling, and control surpasses anything currently in service with any air force in the world." Air Commodore Sorley approached Smith, his expression transformed from skeptical authority to restrained admiration. The successful test flight had vindicated not only the technical approach, but also the strategic decision to pursue unconventional solutions to seemingly intractable problems. "Mr. Smith," Sorley said formally, "I believe congratulations are in order. Your counter-rotating propeller system has exceeded our most optimistic performance predictions." The question now was how quickly production modifications could begin for operational squadrons. As the small group of engineers and officials gathered around the modified Spitfire, Smith felt the satisfaction of being proven right, yet it was tempered by the awareness of the immense challenges that lay ahead. Proving his system worked was just the beginning. Turning experimental success into a battlefield advantage would require manufacturing precision, pilot training, and logistical support on a scale that would test Britain's wartime industrial capacity to its limits. But in this moment, standing beside the aircraft that had transformed his radical idea into a demonstrated reality, Smith allowed himself to imagine counter-rotating Spitfires dominating the skies over Europe. Their incredible speed and maneuverability would provide a superiority that could determine the outcome of the war itself.